Hello, my name is Fernando Soldevila, and today I'm going to show you our last results regarding multispectral fluorescence lifetime imaging using single pixel detection in combination with data fusion techniques. So when I think about a multidimensional image, usually I think about a two-dimensional image with some additional physical information. So for example, it could be polarization, it could be wavelength, it could be depth, or any other physical parameter that you might think about. And this is really interesting because this additional information is very useful. So for example, we know that multispectral information is related to the chemical components of the scene, so it's widely used in bioimaging. In the same way, polarization gives you structural information, so it can also be used in biomedical imaging, but also in detecting defects, for example, in transparent pieces. And of course, depth and time are widely used in vivo studies of full specimens. So while this is very interesting because it gives you a lot of information, it's not really straightforward to build a system that allows you to gather information both in, for example, spectrum, polarization, and also depth or time. Because you could think about, okay, I just need to put everything together and it will be a very nice system. This is why I make the analogy with a philharmonic orchestra. But you cannot just put all the musicians there and expect to get a very good result. There's a lot of conditions that need to be accomplished. So usually when you try to do these kind of systems, if you are not careful enough, instead of having this nice system that is highly dimensional and highly specific, you end up with something that it's not so good. I mean, you will have a system that it's able to measure many different dimensions, but it will not be the best in any of those. And this is due to the fact that you have many trade-offs that you have to take into account when you build these kind of systems. So you cannot have a lot of pixels, a fast system with many wavelengths, very sensitive at low price, and having no problems in storage and transmission when gathering these huge datasets, highly dimensional datasets. So what can you do to tackle these problems? So for the last years, we've been exploring these kind of single pixel techniques, which are quite promising in the sense that they allow you to build multidimensional systems in a very efficient way. So the main difference between a single pixel camera and a conventional camera is the fact that you just use a single pixel detector instead of an array of detectors, and you project structured illumination patterns onto your object, and for each pattern you collect the intensity with a bucket detector. This is nice because you can use very specific single pixel detectors that allow you to measure, for example, in very low illumination conditions, or you can use time of flight detectors to gather 3D images, etc. So for example, here I show some of our last applications doing multispectral, polarimetric, phase, or 3D imaging. And while these systems are very good, all of them share the same problem, and is that the measurement process is sequential. So if you want to take images with a high number of pixels with very high resolution, you need to spend a lot of time measuring. And there are several ways of tackling this problem. Today I'm going to show you one based on data fusion. So for those of you that do not know data fusion, the idea is quite simple, and it's just to gather multiple datasets by using different sensors and then combine them using some kind of algorithm, so doing it in a clever way to obtain a richer dataset than any of the individual ones, any of the starting ones. So this has been used a lot in remote sensing because there, for example, you can have different planes or satellites taking images of the same surface, and then you want to merge this information to do very deep analysis on the surface. It's been also used recently in self-driving cars because they have many different sensors. They have radar, LiDAR, and visible cameras. So you need to gather all this information in order to be able to drive by itself. And also in biomedical imaging, it's been used recently. Here I just put an example of a data fusion between two images, one obtained by fluorescence microscopy and another one by atomic force microscopy. So what we want to do here is to do time-resolved multispectral fluorescence imaging by combining single pixel cameras and pixelated detectors. And we hope that by doing this way, we can get the best of both worlds. So basically, when you have a pixelated detector, you get very high spatial resolution in a single shot, which is nice, but you're able only to measure intensity. With a bucket detector or with a single pixel camera, you can be very specific in the parameters that you measure, so you can easily build the multispectral or time-resolved systems, but the acquisition is low and the spatial resolution is not so high. In the same way, when you do conventional multidimensional imaging, the datasets that you acquire are super big, because you are gathering information about many different parameters. But when using data fusion, you can try to compress in the measurement process. So you gather not a lot of data, and you let the algorithm fill in the gaps for you, similar to the way compressive sensing works. So how do we do it? This is our experimental setup, and I'm going to show you step by step how we obtain an image. So first we have the excitation laser, which emits pulses of light, and these pulses illuminate the object, which corresponds to 3 different letters in this case. Each one is a different fluorophore species, so each one of the letters will emit a fluorescent signal in different wavelengths, and also it will decay differently over time. So after we illuminate the object, we measure the object with 3 different cameras in parallel. So the first camera is a conventional pixelated camera. It's just a CMOS detector, which will take the projection of our 4-dimensional object in the real space. So we integrate over time and over spectrum, and we get a monochrome image of the object. After this, or well, in parallel to this, we image the object onto the SLM, and we have 2 single pixel cameras working on the reflection arms of the SLM. So the first single pixel camera is a multispectral single pixel camera. So our detector is just a fiber spectrometer, so we collect the intensity in many different wavelengths when we put all these structure patterns that I was talking about before. So basically this camera will gather a 3D image, which will be X, Y, and lambda, and we do the same with a different detector. Now we are not detecting different wavelengths, but we put a really fast detector here, so we are able to resolve the fluorescence decay of the scene. So after gathering these 3 data sets, we just need to recover the object that corresponds to these measurements. And this is just an inverse problem that we can solve by using gradient descent. Basically, what we do is we formulate an objective function which has 3 different terms. Each one is a data fidelity term for each one of the cameras. And basically, we minimize this to find the 4D object. We calculate the gradient, and then we update the solution until we converge. So this is the data sets that we acquired. First, we have the CMOS image, which is high resolution. You can see that there is a lot of detail here. And then we have these 2 datasets, which are the single pixel camera datasets. So here we have a 32 by 32 pixel multispectral camera. We have 16 different spectral channels. So the spatial resolution is much lower here, but we have the information about the wavelength. And in the same way, the spatial resolution here is very low, but we have 256 frames, each one with about 50 picoseconds. So overall, we measure for about 25 nanoseconds. So after we gather these 3 data sets, we feed that to the data fusion algorithm, the minimization I was talking to you about before, and then this is the results that we get. So here you're watching the full object in the 16 different spectral bands. And when we illuminate the object, you see that the fluorescent signal for each one of the letters, that are these 3 graphs, you see that when the pulse arrives, the fluorescence starts to emit, and each one of the letters presents a different decay time. So the U letter has a very fast decay time, and both letters J and Y, which are different fluorophores, have a different decay time. So here I want to show you which is the improvement in resolution that we get. So here, for example, you can see the 3 data sets that we gather again. And here I put 3 insets in order for you to see the quality of the spatial resolution of these original datasets. And this is the result from the data fusion recovery. So you can see that we have the full 4D information because we have the maps of wavelength versus time for each one of the letters. And you can see clearly that we have improved a lot in the spatial resolution with regard to the single pixel cameras. Also here you can see both the temporal decay of each one of the fluorophores and the emission spectrum for the fluorescence. So compared with the ground truth measurements. So one last thing is that as I was telling you before, one of the problems of this kind of highly dimensional systems is that you gather a lot of data, and it can be a big problem if you need to do a lot of measurements. So for example, this experiment that I showed you just now, the number of voxels on the object that we recover is basically 1 giga. So if you use 8 bits per voxel, the dataset is around 8.5 gigabytes. But actually, the number of measurements that we did is just the CMOS camera, which is 512 by 512, and then the 2 single pixel images, which are low spatial resolution, 6 till spectral bands, and 256 temporal bins. So this is about 4 megabytes. So basically we are recovering an 8.5 gigabyte dataset, but by just measuring 4 megabytes. So we have a compression ratio which is extremely high, and this allows us to gather very good quality images. If you compare with the images that you could take with just with the single pixel cameras, because you could do this just with single pixel cameras, but it will take more than 200 times longer to acquire this. Of course, then we need to do the recovery process, which takes some time, in this case 40 minutes, but this is implemented only on the CPU and is not really very optimized, so this could be much shorter. And okay, just to conclude, I just wanted to say that I presented some data fusion techniques. We have used these data fusion techniques to improve the performance of, in our case, a 4D imaging system. We have improved the acquisition speed and reduced the dataset size that we take. The results shown here are two-dimensional in space, multispectral and time-resolved, but this is a general concept that can be applied to many different systems. So if you want to measure polarization, phase, depth, or any other parameter, you can apply these ideas. And the simplicity of our approach, we think it's a nice thing, but of course you can introduce more sophisticated methods which will decrease the computing time, for example, based on machine learning or implementations on the GPU. And of course you can complicate a little bit the model-based recovery by adding sparsity terms, for example, which will increase the quality of the reconstruction. So I just want to say thanks to the people involved in the project, Armin and Enrique in Spain, Alberto, Andrea, and Cosimo in Italy, and of course the people who put the money, and all of you for your attention. Thanks.